A functional group is a feature or a particular structure on an organic compound that gives that compound a special characteristic or some sort of special property. In Chemistry 11, we go over the 8 main functional groups in organic chemistry, and you will be expected to memorize and recognize all 8 types. So an example of a functional group that you may know of is an alcohol. In Science 10, you learned that alcohols all have an OH group on them, and that particular OH group is what gives that alcohol its properties, such as its strong odor, its flammability, its easiness to evaporate, and its poisonous property. Yes, alcohols are poisonous, that's why you get wasted. So the first one we're going to look at is an alcohol. And alcohols, remember, have an OH group. So I'm just going to draw one example of an alcohol. Okay, there's the OH group right there. If I were to draw this in a condensed structure, I would draw CH3 for that one. Oops. CH2 for this one. CH2 again for that one. The next one is not CH2, but it's just CH, because remember, each carbon can only have 4 bonds. And since we have an OH group attached to that carbon, one of the H's must be lost. Followed by OH next, and then CH3 right there, rounding it off. Okay, so the particular features of this molecule that make this an alcohol is this group right here, and you can find it in a condensed structure as an OH embedded in the middle of a structure. And properties, once again, they are poisonous, and they have a strong odor or strong smell. I'll put strong smell. Okay. The next functional group is called a ketone. It looks similar to an alcohol in that it has an O bonded to the carbon chain, except this time the O is bonded with a double bond and there is no H right beside it. It's a ketone. If I were to draw the condensed structure, it would look like this: CH3, CH2, CH2. When we hit this carbon here, that carbon has a double bond O, so it does not have any room for H's on it, so that would just simply be CO, CH2, CH3. And the features of this compound that make it a ketone is this group here, and the CO within a carbon chain. Ketones, they are found in sugars. Lots of sugars have them, found in sugars. And they are good for synthesis. What we mean by that is organic chemistry is all about chemical reactions. Mixing chemicals together and they somehow react with each other, they combine and form new substances. And most of the compounds that we learned so far, the alkanes and benzenes, the cyclic alkanes, alkenes, alkynes, those are all rather stable, meaning that they don't react quite well, which is bad for organic chemistry. So a lot of times we don't start with alkanes and alkenes as the starting ingredient for a new compound. We actually start with something that has a functional group to it, and one of them is a ketone. Oxygens, we know that they are highly electronegative, and that means that the oxygen gives this particular compound a certain level of reactivity. This oxygen is so electronegative that it can pull or draw electrons from other compounds, meaning that it can react with other compounds. So ketones are good for synthesis, and you will find them as precursors or starting reagents and reactants for many pharmaceutical compounds. Okay, next one is an aldehyde. An aldehyde looks very, very, very similar to a ketone in that it has a C double bond O, but right next to the carbon that has the double bond O is a hydrogen. In other words, aldehyde is a ketone but located on the first or last carbon in a structure. Okay, aldehydes, the condensed structure looks something like this: CH2, CH2, C, O, then H, or sometimes you will find them looking like this. CH2, CH2, CHO. So the structure you're looking for to classify a compound as an aldehyde is this group right here. It will look like a COH at the end of a condensed structure, or CHO. Some properties, not a lot of properties to take a note of. It's just that they are also good for synthesis. Okay, next up we have the carboxylic acids. The carboxylic acids look like ketones again with the double bonded CO, but this time right next to that carbon with the double bond O, we have a OH group. In a condensed structure, it would look like CH3, CH2, CH2, C, O, O, and H. So the component of this structure that classifies it as a carboxylic acid is this grouping here. In a condensed structure, it will look like COOH at the end or the beginning of a condensed structure. Hey, that was familiar. COOH. Remember everyone's favorite molecule, CaCHO? Well, now you know what CaCHO looks like at the very, very end. Carboxylic acids, we call them organic acids. Now, acids are very useful in synthesis. And we have learnable acids in the form of these ionic acids here, like HCl, HBr is another example, H2SO4. All the acids we've seen in Science 10 have all these H's at the beginning of a compound. This acid is an organic acid. Organic acids are not ionic in nature, they are covalent. And the H that's important, or the H that gives this molecule its acidic behavior, is this H right there at the very, very end. So back in the beginning of the year, some of you asked me, why is CaCHO written like this with the H at the very end? Why isn't that H located at the very beginning of the molecule? Because structurally, when you draw the molecule out, that H, the important H that makes it an acid, is actually located at the very, very end of the molecule. So now you know, everything is starting to make sense. Next molecule we're going to look at, next functional group is called an ester. Esters also have the double bonded CO. Let's try that again. There we go. Boy, that sure is popular, that grouping. But right next to carbon with double bond O is a oxygen, which is then attached to more carbon chains. In a condensed structure, it will look like this: CH3, CH2, CH2. Then we have a COO motif in the middle, followed by another chain. So this is the feature that makes the molecule an ester, a CO, CO in the middle of the chain. Carboxylic acids, the CO is at the very, very end, and esters, the CO is in the middle. Some special properties of esters: they smell. Sometimes nice, sometimes not. When it smells nice, for example, the banana scent, the apple scent, those are all ester compounds. But you know, at the same time, the paint smell is also an ester. So esters, they are fragrant. They smell pretty strongly. Next, we have ether. I like ethers. They look so happy. It's a happy face. In a condensed structure, CH3 will look like this: CH3, CH2, O, CH2, CH3. So how you identify an ether is you're looking for this O right in the middle of some chain. It doesn't have to be right in the middle. It can be off-center too. But when I say middle, I mean it's flanked by carbons. Okay, ethers. Here's the reason why they look so happy. Ethers are an anesthetic. And anesthetics are, of course, compounds that cause you to sleep or get knocked out. They are used in surgery, so that's how I remember them. Ethers look happy, and they are an anesthetic. Next, we have amine. Amines are compounds that contain nitrogen, in particular NH2. In a condensed structure, it will look like this: CH3, CH2, CH2, C, N, H. Whoops, I missed an H there. CH, NH2, CH3. And the feature that makes it an amine is that thing right there, an NH2 in the middle of a condensed chain. Now, amines don't have to have an NH2 as a branch. It could have the N in the middle of a chain, but in Chemistry 11, we only talk about the most simple amines, which are ones that are just a branch of NH2 coming off a main chain. Amines are what we refer to as an organic base. They have basic properties. I know in Science 10 you learned that all bases have OH in their formulas, for example NaOH. Later on though, in Chemistry 12, if you take that, you'll learn that bases can look different even if they don't have an OH group. So an amine is an organic base. It would indeed turn red litmus paper blue if you tried. Another property, they smell fishy. Oh, that's nasty, isn't it? You kind of have this fishy odor. If you were to eat a lot of meat and didn't drink enough water, your urine would be quite concentrated, quite yellow, and it would smell pretty horrible. And that particular smell is coming from the amine compounds in urea in your urine. That particular compound comes from the digestion of meat, which has proteins in it, and when you digest and break down proteins, you release these compounds that have amines attached to them. Doesn't smell really nice. But hey, here's some trivia for you. Why is it that when we cook seafood, we put so much lemon all over the place? Why do we spritz our crab and shrimp and salmon with all that lemon juice? What's up with that? Well, people don't really like the taste of the fishy smell. They don't like the fishy smell at all. Have you ever had a microwave food thing and then it smells like fish because the person before you had microwaved some salmon in there? Not so very good. Well, because the fishy smell is an organic base and lemon juice is an acid and base is neutralization. So you've reacted the amine out and turn it into, water and whatever other compound that comes from neutralization. So that is why. It's not my why. So next time your parents make you fish and you're putting that lemon on there, you can say to them, hey, you want to know why that works? I can tell you. Oh, they'll be so impressed. Last compound. Speaking of proteins and protein digestions, we have amides. Amides, they also have the NH2 group. Amine, amide, they kind of sound similar, so that's kind of nice. But right next to the amine group, they have a, you guessed it, C double bond O group. And that's an amide. In a condensed structure, it will look like this: CH3, CH2, CH2, CONH2. So the particular thing you're looking for to see if it's an amide is this little structure there, or a CO and H2 at the beginning or the end of a condensed structure. What's so special about these guys? They are found in proteins. If you are taking Biology 12, you are going to be studying proteins and amino acids, and you'll learn that amino acids joined together form a peptide, and the peptide bond is just an amide bond. So a protein structure is just a long chain of amino acids joined by these amide bonds. Amides can also be in the middle of a chain, but again, in Chemistry 11, we only study the ones that are on the first or last carbon to make things simpler and to make naming a little bit shorter. Okay, so those are the 8 functional groups in organic chemistry that you will have to learn to recognize, and memorize, and identify. Let's try some of that out. Phew. Here is a structure for household white vinegar. That's Kachu. What functional groups do you see in this particular structure? Well, you might say that, oh, I see a ketone, a C double bond O, but that would be incorrect. That particular C double bond O is right next to this OH group here, and altogether, this is what we refer to as the carboxylic acid functional group. Let's try another one. Here is the structure for aspirin. So for all you guys taking painkillers out there, this is what aspirin looks like. Before we talk about the functional group, remember what that is? This is our benzene ring. Okay. Alright, what are our functional groups? Again, we see this thing over here, which is the CHO part in CHO, and this is the carboxylic acid. There's one more functional group in here, and that's this guy. What is that? That is a C double bond O next to an O in the middle of a chain. This would be our ester group. Okay, so that's what we have to be able to do with functional groups. We have to learn how to recognize them when we see them, call them by their correct names, and also memorize some of their particular properties. Okay, all right, that's it for functional groups. Go out.